Okay, we are ready for the fundamental theorem of algebra, and we're going to learn a few other theorems that help us. And so, the fundamental theorem of algebra was first proven by Gauss, and he was only 22 when he did it. So there's a little picture of him, and he contributed to huge contributions to the areas of math and engineering and science. So he is a very big figure. So I thought his picture deserved to be right there. He looks a little bit like Christmas Carol guy from that movie. Anyway, the fundamental theorem of algebra states that every function defined by a polynomial, so any polynomial of degree 1 or more, has at least one complex zero. That's all it says, but it's very significant. So basically, a polynomial, if it's of degree 1 or higher, so a line, a parabola, a cubic function, a quartic, anything like that. If it's 1, it has at least one zero. And so the zero is complex, so a plus bi. This is a complex number. So that means that the zero of this 1 degree polynomial or higher could be real, meaning it just has a where b is 0. It could be purely imaginary, bi, or it could be have a real part and an imaginary part. It could have all of those things. Okay, so but the significance of this is that of degree 1 has at least one zero. From that we build all these other theorems. And so here's the one that you guys have heard probably a lot, is that if you have a polynomial, so here's just some, let's say we've got y is 3x plus 2. Y is 3x squared plus 2x plus 1. Y is 3x cubed plus 2x squared plus x plus 4. Okay. This one is to degree 1. It's going to have, if I set this equal to 0, it's going to have one solution. This is to degree 2. If I solve this as an equation, it's going to have two solutions. This one is to degree 3. It's going to have three solutions. Now, these solutions might be real, might be imaginary, might be a combination of real and imaginary. Those are complex. And so from the fundamental theorem, we get this one that we're really familiar with. I'm sure your teachers prior to me said, how many solutions will this have? And you say, oh, 1. How many solutions will this guy have? 2, and so on. So that's how we build that, and that is called the number of zeros theorem. And so the next theorem I want us to look at is the rational zeros theorem. This is one that you probably have heard of before, but you know, just if it might have been a while. I copied this down on my page. If you have a polynomial p of x, written like this, a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on. These a's are the numbers in front, the coefficients. This is x to the 1, x to the 2, x to the n minus 1, x to the n. By the way, from the zeros theorem, the number of zeros theorems, this will have n solutions because that's the power. But what the rational zeros theorem does is it helps us start to build a possible list of zeros, roots, solutions, x-intercepts. That's what those are. So we can form a list of possible zeros, rational meaning fractional. And so how you form this list, and these are not all going to be zeros, but it's the ones we can choose from that will help us good choices. And so if they do exist, they'll be on this list. It's the factors of the last term divided by the factors of the first term. And we can form a list to choose from that helps us narrow the search. So the search for zeros is all the real numbers, an infinite amount of numbers. And we need to sort of narrow this down. So we narrow it down using these theorems. First we say, well, how many are we looking for? Using the number of zeros theorem, we're like, well, we're only looking for n, right? So if we look at this one, how many are we looking for? We're only looking for 3. We don't have to keep looking after we find 3. Well, how do we even begin the search? Well, the list of possible rational zeros helps us begin the search because these are good numbers to choose from. So I'm going to show you how to do that. There are other theorems that I'm not going to be teaching you, but I want to mention to you. The other theorems, one is Descartes' rule of signs, and what it does is it helps you determine the number of positive or negative real zeros that the polynomial might have. So it doesn't help you find the negative ones, but it kind of narrows your search. Okay, here's a list, and from that list, If we know it might be, this many might be positive, we know to choose the positive ones. Or this many might be negative, we know to choose the negative ones. Then there's another theorem called it's called the Boundedness Theorem. Yeah, I can hardly say boundedness. But it helps give you a bound between what's the highest number these zeros can be and what's the lowest number these zeros can be. Now these theorems apply to real zeros, so if there's imaginary part to these, then those don't apply. But if you can pick out the real ones, if they happen to have imaginary roots, that narrows it down and you can help search for those. So these are helpful. Now, I'm not teaching the other theorems, Descartes' rule of signs and Boundedness theorem, because I don't think that we need to learn them because we have graphing calculators. But I did not want to dismiss the rational zeros theorem. And then there's another little technique called the negative one test I'm going to teach you. So we're just going to dive into it, and as we dive into it, you're going to see how these theorems work. I have put the 4 problems that I gave you on the worksheet on this board. And so the instructions for these problems say, first, make a list. Use the rational zeros theorem to form a list of possible zeros. So we're gonna apply the rational zeros theorem to 1, 2, 3, 4 problems. Okay. Then it says use the negative one test. So I'm going to show you how to do that. And finally, it says find all of the zeros. So how many are we looking for? Let's just look at that. How many zeros are we looking for? For number 1, there's 3. We're going to find 3. For number 2, there's also 3. For number 3, we're also looking for 3. And for number 4, we're looking for 4. Okay, so this will illustrate how this goes. Of course, this could be applied to polynomials of degree 1, 2, 6, 7, 5, whatever degree. But these are the ones that I think will demonstrate that. All right, number 1, we're going to apply the rational zeros theorem, and we're going to form a list of possible zeros. All right, so real zeros. So this is not all of them, but this is a good choices, is what it does. So the list will equal to plus or minus the factors of the last term, -1, over the factors of the first term, 3. Now, whether these are positive or negative doesn't matter because we're going to take the positive and negative of both of these. So this is how you think about this. What are the factors of 1 or -1? It's 1 times 1, basically. What are the factors of 3? It's 3 and 1. So this is going to be my list. It's going to be plus or minus 1 divided by 3, 1/3. 1 divided by 1, 1. So this negative, don't even worry about the negative because this plus or minus captures them all. So although this looks like a list of 2 numbers, it's a list of 4. 1/3, this is what it really is, -1/3, 1, and -1. This is the full list. Now I don't mind if you write it like that, but that's how we would apply the rational zeros theorem to number 1. Let's go to number 2. How could we apply it here? All right, well, the possible list is going to be plus or minus factors of 50 divided by factors of 1. The coefficient of leading term is 1. All right, well, let's see. This is going to be plus or minus. What are the factors of 50? 1 times 50, okay. 2 times 25. And 5 times 10, and there aren't any factors in between 5 and 10. Over factors of 1 are just 1. All right, so this is not my list. This is, when I got to divide 1 into this, so this would be a cleaner list. Plus or minus 1, 2, 5, 10, 25, 50. All right, so that's 1, 2, 3, 4, 5, 6, really 12 positive ones, negative ones. That's 12 possible zeros. Now, obviously, all of those are not zeros. There's only 3, but this gives us a good place to start looking. It narrowed it down from an infinite number to 12 to start looking, so that's pretty good. All right, right here, 3 possible factors of 10. All right, what are factors of 10? 1 times 10, 2 times 5, and I think that's it. All right, factors of 1. All right, so really it's plus or minus 1, 2, 5, 10. That's 8 possibles that we could look at. All right, over here, factors of 2, plus or minus. Factors of 2. What are the factors of 2? 1 times 2, okay. factors of 6. What are the factors of 6? 1 times 6, 2 times 3. All right, so let's list these out. This is the most complicated one. So this is how it goes if you have one where you don't have a really easy coefficient. 1 over 1, 2 over 1. Okay. 1 over 2, 2 over 2. But 2 over 2 is really 1, so we already have that one. Okay. 1 over 3, 2 over 3. 1 over 6, 2 over 6, but that's really 1/3. It's already on the list. So 1, 2, 3, 4, 5, 6, really 12 possible ones right there. Okay, so that is how you apply the rational zeros theorem. That was number 1. Number 2, use the positive, negative 1 test. So this is something I read in a textbook, and I was like, this is a really good test. I don't know why nobody ever taught me this, so I'm teaching it to you because it's cool. To figure out if 1 is a root of this, if positive 1 is a root, what you do is you just add up the coefficients. And if they equal to 0, then 1 is a root. To figure out if negative 1 is a root, you you add up the coefficients, but you change the sign of the odd powers. So for instance, an odd power is x cubed. I would change this coefficient to -3. So I'm just going to go through and do this one, and you'll see how it works. This is, I'm going to erase this other, in a minute I'll erase this other stuff. So P1 of 1 and P1 of -1. How does this go? All right. To find find P1 of 1, just simply add up the coefficients. 3 plus 1 plus -3 plus -1. 3 plus 1 is 4, plus -4 is 0. Wow, already x equals to 1 is a root. That was pretty easy. Let's try the -1 test. Add up the coefficients, but if the coefficient is odd, if the power is odd, change the sign. So instead of 3, we'll say -3 plus 1. This is odd, x to the 1, plus 3 minus 1. This is going to give me -2 plus +2. Oh, this one also equals 0, so x equals to -1 is a root. Look, just like that, we ticked off 2 roots. We just have 1 more to find. Okay, so let's go through and do the positive, -1 test for all of these and see what we can figure out. P2 of 1 goes like this. All right, just add up the coefficients. 1 plus 2 minus 25 minus 50. That's -75 plus 3. This is -72. This does not equal to 0. So what I know is that x equals to 1 is not a root. All right, it's not a root. What is P2 of -1? Well, go through and add these up, but change the sign if the power's odd. So this is going to be -1 plus 2, change the sign, plus 25 minus 50. This is going to be -51 plus 27. Oh, what in the world is that? It's not 0, is it? That's a 4, that's an 11, that's a 4, -24. But since that's not 0, what we know is x equals to -1 is not a root. Okay, well that one wasn't as helpful, but what that tells me is don't bother messing with trying to see if that's a root because we already know it's not. Okay, let's go on to P3. P3 of 1 is going to be 1 minus 2 minus 13 minus 10. This is -23, -24, -25 plus 1, -24. Okay, what that tells me is it did not equal to 0, right? So x is 1, not a root. All right, P3 of -1, change the sign, -1. Don't change the sign. Change the sign, 13. Don't change the sign. So this is -13 plus 30. Oh, this equals to 0. Yay! So this tells me that x equals to -1 is a root. That was helpful. Okay, let's do this one. P4 of 1. 6 plus 7 minus 12 minus 3 plus 2. 13, 14, 15 minus 15. This is 0. This tells me that x equals 1 is a root. That's great. We have to find 4 of these. We've got 1. P4 of negative 1 is going to be 6 minus 7 minus 12 plus 3 plus 2. Let's see. Keep, change, keep, change, keep. That is negative 19 plus 9, 10, 11. This is negative 8, which is not 0. So x, negative 1, is not a root. Okay, so that's how you apply the 1, negative 1 test. So now, finally, we're supposed to figure out what all the roots are. So let's go through. I'm going to have to make some room, so I may erase some stuff as I go. Number 1, we listed the factors. Okay, that was this guy. Good. This is the factors. We did the 1, negative 1 test, and what we found out that 1 is a root and negative 1 is a root. That is so helpful because this is our list of possibles, and we already found out that 1 and negative 1 are roots. So we just got to find the third root. So how will we do that? We will do that through synthetic division. Do you remember the factor theorem and the remainder theorem? That has to do with roots that we can find. So we already know, I'm going to erase this just because of room. If this was a test where I said do all this stuff, you got to show me that you did all that stuff. You wouldn't erase it afterwards. You would leave it on there so I could give you credit. Okay, so, but we know this. All right, so 1 is a root and negative 1 is a root. What can I do? Well, if I know this is a root, then what I know is that if I run this through an iteration of synthetic division, my remainder will be 0. And it can help me start to factor this guy. So let's do that. 1, synthetic, 3, 1, negative 3, negative 1, 3, 1, negative 3, negative 1. Bring down the first guy, 3. Multiply up, 3. Add down, 4. Multiply up, 4. Add down, 1. Multiply up, 1. Add down, 0. That's what I knew would happen. So what this means is that P1 of x can start to be factored, okay? We know that x minus 1 is a factor. But what I can do is build off of these three numbers. Now I take the one I haven't used, negative 1, and divide it into this. This is 3x squared plus 4x plus 1. So we'll put 3, 4, 1. Bring down your first guy, multiply up, negative 3. Bring down, add down, 1. 1 times negative 1 is negative 1. I was expecting this because I already knew that was a root. So this is good. X, back it into factor form. X minus negative 1 is x plus 1. Okay, what are we left with? We're left with 3x plus 1 times 3x plus 1. This is factored form. But from factored form, it's so easy to see the roots. Ready? X equals to 1. X equals to negative 1. And this last one, if you set that equal to 0 and solve, x is equal to negative 1/3. These are the three roots for number 1. All right, cool. Let's move on to number 2. What we knew about number 2 is that basically 1 and negative 1 are not roots because that didn't yield anything. Okay, so what we do is we just try to work on it from there. We have this nice little list that our rational zeros theorem gave us, the positive and negative numbers. And so here we go. We know we don't need to try 1. We already know he doesn't work. Let's go for 2 and see what happens. 2, let's run it through synthetic division. If we can get a 0 right there, we're in good shape. So let's see. This is going to be a 1, 2, negative 25, and negative 50. Let's just see what happens. Bring down 1. 1 times 2 is 2. Add down 4. 4 times 2 is 8. Add down negative 17. Negative 17 times 2 is negative 34. Add down negative 84. This is not a 0. That is not a root. So x is 2 is not a root. Let's try negative 2. See what happens. Negative 2. 1, 2, negative 25, negative 50. All right, bring down the 1. 1 times negative 2 is negative 2. Add 0. 0 times negative 2 is 0. Add negative 25. Negative 25 times negative 2 is 50. Add 0. Oh, we finally got one. Okay, so x equals to negative 2 is a root. If we begin to factor P2 of x, right, we get x back and in two factored form plus 2 minus negative 2 is how you think of that, times what? Times this. Times x squared minus 25. Well, hey, I can factor that. That is difference of squares. So I'm going to stop and factor this, but if you wanted to, you could also just start going through all those positive 5, negative 5, positive 10, negative 10, until you get all your zeros to see if they're on that list. Now, keep in mind, some of these might be imaginary, so they are not required to be on there, but it's the good ones to choose. So this is going to work out great. X plus 2, x plus 5, x times negative 5, that gave me the ability to factor this guy. And so from the factored, I can pull out what the roots are. It said find the roots, or the solutions, or the x-intercepts, 5 and negative 5. So those are the 3 for number 2. All right, great. Let's go down here to piece of 3. What we found out here with the 1, negative 1 test was that 1 was not a root, but negative 1 was a root. All right, let's build off of that knowledge. Negative 1 is a root. Cool. All right. So let us run him through synthetic division and see what happens. So let me make a little more room. Let me just take note of this. X equals to negative 1 is one of my answers. Let's do a little synthetic division. Goes like this. We'll say negative 1. Coefficients 1, negative 2, negative 13, negative 10. Bring down the 1, negative 1, negative 3. 1 times negative 3, 3, negative 10, 10, 0. We knew that was going to happen. We could try to plug in other roots to see what happened, or we could just build off of this knowledge that P sub 3 of x is equal to, back this into factored form, x plus 1 times what? Times x squared. Remember, this is the remainder. X to the 0, x to the 1, x to the 2. This is x squared minus 3x minus 10. Now, if this factors, great. If it doesn't factor, great. We know quadratic formula. So let's see. I think this does factor. X squared minus 3x minus 10. Yeah. So this, if you were able to factor it, it's really easy to pop out the roots. X is negative 1 is 1. X is 5 is the second one. X is negative 2 is our third one. Now, what if we had just continued down our list of rational numbers, like our purple list that I erased? We would eventually find 5 and negative 2 because they were on that list. So you could also do it that way. Okay, let's do number 4. I'm going to make a little more room up here because there's 4 roots I have to find, right? I got to find all 4 of them, so let me see. Oops, did I mean to do that? I did not mean to do that. Now I got to make my new list. All right, let me just do 4 from, let me just catch up. Let me rewrite it up here. P sub 4 of x was right here. P4 of x. This is not even the right worksheet. Where did you go? Oh, yeah, it is. It is, what is it? A 6, x to the 4th plus 7, x cubed minus 12, x squared minus 3x plus 2. Okay. Just do the whole thing real quick. Rational zeros are plus or minus the factors of 2. Let's see. 2 and 1 over 1 times 6, 2 times 3. All right, so if I had to list them, which they did, this is going to be plus or minus 2 over 1, 2 over 2, 2 over 3, 2 over 6, which is 1/3. And then 1 over 1, which I already have 1 on the list, 1/2, 1/2, 1/3 already on the list, and 1/6. All right, so this is the possible list. Okay, then I said P4 of 1 is going to be 6, 7 minus 12 minus 3 plus 2, and I said this is 0, so this x is 1 as a root, and I think P4 of negative 1 was 6 minus 7 minus 12 plus 3 plus 2, which was negative 19, negative 8 or something like that. It didn't equal to 0, so x equals to 1, not a root. Not a root. Okay, so we're going to build from here. Start with what we know is a root. X is 1 is a root. So let's do that. 1, go through synthetic. 6, 7, negative 12, negative 3, 2. Bring down your 6. This is 6. This is 13. This is 13. This is 1. This is 1. This is negative 2. This is negative 2. This is 0. We knew this would happen. We would expect this to happen. If you did not get a 0 when you're plugging in a root, there's a mistake. Either it's not really a root, you made a mistake in choosing that as a root, or you made like an error in your synthetic. So we know that'll be 0 if it's a root. So that's good. Let's build off of that. Now what we can do is we can work with these. So what I'm going to do this time is start picking off of this list right here. Okay, let's just record x equals to 1 is one of our answers. Okay. X equals negative 1. Okay. X equals 1 is one of my answers. So let's build off of that. Don't pick 1 or negative 1. We've already dealt with him. Let's pick 2. It's the only other whole number. Let's see what happens there. 2, but this time we'll go off of this lower list. 6, negative 13, 1, negative 2. Bring down the 6. This is 12. This is negative 1. This is negative 2. This is negative 1. This is negative 2, and I get negative 4. 6, 12, negative 1, negative 2, negative 1, negative 2, negative 4. Okay, 2, not a root. All right, well, let's try negative 2. Plug in these same 6, 3, 1, negative 2. I mean 13. 1, negative 2. All right. 6, negative 12. Wait, something's not right here. Oh, this is not right. I put negative 13. This one. Let's see what happens here. That's right. Bring down your 6. This is 12. Oh, wow, that's 25. That is a 50. That is 51. That is 102. My remainder is 100. Okay, I got the same result. This is not 0, so x equals to 2 is not a root. Okay, good. But I need to plug in the right numbers. 6, 13, 1, negative 2. We're trying negative 2 this time. Bring down your 6. 6 times negative 2 is negative 12. This is a 1. This is a negative 2. This is a negative 1. This is a 2. Oh, we got a 0. Great. X equals to negative 2 is a root. Well, what is this? This is a remainder. X to the 0. X to, no, that was x to the 0. X to the, yeah, 0. X to the 1. X to the 2. Let's try to factor P4 of x. It factors into, back this into factored form, x minus 1. Back it in, x plus 2 times x, 6x squared plus x minus 1. Now, if I can factor that, great. If I can't factor it, great. I can use a different method. This doesn't factor. I'm going to use quadratic formula. So quadratic formula says x is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. All right. So this is going to be x is negative 1 plus or minus the square root of 1 plus 24. Is that right? Yeah, 24 all over 12. X is negative 1 plus or minus 25 over 12. Negative 1 plus 5 over 12, negative 1 minus 5 over 12 gives me 4 over 12, or 1/3. Another root. Was it on the list? Yep, we could have found it if going through synthetic if we had chosen to. Negative 1 minus 5 is negative 6 over 12, or negative 1/2. Is it on the list? Yeah, these are plus or minus. So these are our 4 roots. Now, what if this was not on the list? We could still find it once we get it down to x squared. Even if it's imaginary, it's fine. We can figure that out using quadratic formula or completing the square. All right, so that is the fundamental theorem.